Welcome back, my curious friend. Tonight, we're going to do something wonderfully strange together. We're going to lean back, close our eyes, and gently walk into one of the most impossible-sounding ideas science has ever put forward. Time travel. Yes, that slippery dream of stepping into yesterday or peeking into tomorrow, of revisiting old memories, not just in your mind, but in reality, or jumping forward to see what hasn't happened yet. It's the kind of thing we usually leave for science fiction, for blue police boxes or shiny DeLoreans with gull-wing doors. And yet, as wild as it sounds, time travel isn't just fantasy. It's a real, thorny, puzzling part of physics. And the deeper you sink into it, the more you realize it might not be as impossible as it first seems. But before we set foot on this strange road, I want you to be comfortable. This isn't a lecture, and you don't need to take notes or stay sharp. You can let your mind wander, float in and out of the words. Some of them might make you laugh, some might confuse you, and some might just wash over you like background music. That's perfectly fine. The journey itself is what matters, not memorizing every twist and turn. So find your cozy spot, maybe under a blanket, maybe with a cup of something warm, and let's begin. Of course, it would mean a lot to me if you tapped that like button before we tumble through time together. And if you haven't already, subscribe and join this little corner of the internet where we take the universe apart one dreamy piece at a time. I'd also love to know in the comments where and when you're watching this. Are you curled up in bed at midnight in New York? Or sneaking in a break at 3 p.m. in Tokyo, pretending to work while secretly traveling across centuries? It's always a joy to see this little community scattered like starlight across the globe. All right, time travel. Where do we even begin? Maybe with the obvious. Time, as we experience it, feels like an arrow. It moves one way. You wake up, eat breakfast, live your day, go to bed, and repeat. You don't slip back into yesterday morning's pajamas or accidentally drift into tomorrow's lunch. But ask a physicist what time really is, and they'll hesitate, because deep down in the equations, time isn't always so clear. Sometimes it looks like it can stretch and warp. Sometimes it looks like it can run at different speeds in different places, and sometimes, in very special circumstances, it even hints that traveling backward or forward in dramatic ways might not be off the table. Let's start gently, with something most of us already know without realizing it. You are, right now, traveling through time. Every second you spend listening to my voice, you're moving 1 second into the future. Not very impressive, I know. It's like bragging that you can walk forward while standing on a moving walkway. But here's where it gets strange. You're not traveling through time at the same rate as everyone else. None of us are. This isn't poetic exaggeration. It's a fact of Einstein's theory of relativity. Einstein showed us that time isn't universal. It bends and stretches depending on your speed and the gravity around you. If you're sitting on Earth listening to this, your time is flowing just a little slower than someone drifting in deep space, far away from any planets or stars. And if you were to hop on a spaceship and race close to the speed of light, time for you would slow down dramatically compared to your friend back home. To you, maybe only a few hours would pass. To them, years might slip by. This is called time dilation, and it's not a thought experiment. We've measured it. Astronauts on the International Space Station age a tiny bit less than we do on Earth. Their clocks tick a little differently. Not much, maybe a few milliseconds, but it's real. In other words, they've already traveled a little bit into the future. So maybe the first truth about time travel is this. It's not just possible, it's already happening. Every time we fly a satellite, every time we bounce a signal off a GPS system, we have to account for it. Otherwise, your phone's map would get confused, and you might end up driving into a lake because space-time bent your directions. But what about the kind of time travel we really dream of? Jumping whole years, decades, maybe centuries ahead. Imagine stepping into a machine, closing the door, and opening it again to find skyscrapers where forests once stood, or maybe deserts where oceans used to roll. Well, physics doesn't slam the door on that idea. In fact, relativity says if you could build a ship fast enough, you could leap into the future as easily as booking a long-haul flight. The catch, of course, is building such a ship and surviving the journey. The energy costs are enormous, the engineering challenges staggering. But in principle, the equations don't forbid it. The future is waiting, and there's a path to it. The past, though, is trickier. Going back, that's where things get slippery. That's where paradoxes creep in, the kind that make your brain ache in the best way. Imagine going back to stop your grandparents from meeting. If you succeeded, you wouldn't exist. But if you didn't exist, who went back in the first place? This is the classic grandfather paradox, and it's just one of many logical knots that appear when we even imagine traveling into yesterday. Some physicists shrug and say, well, maybe that means it's impossible. Others say no, maybe it just means the universe has clever ways of protecting itself, like only allowing time travel that doesn't break consistency. You can go back, but you can't change things in a way that creates contradictions. You're free to try. But the universe always finds a loophole to stop you. One of the most famous ideas comes from something called closed time-like curves. Sounds intimidating, but picture it this way. Normally, your life is a straight line from birth to whatever comes next. A time-like curve is that line bent around, looping back to an earlier point. In relativity, under very exotic conditions, such loops are theoretically possible. A path through space-time that lets you end up where you started, not just in space, but in time. It's not science fiction. It's right there in the math. But creating those conditions would require things like negative energy or wormholes held open by exotic matter, stuff we haven't even proven exists. And yet, the possibility lingers like a tantalizing whisper. It's funny though. Time travel might sound futuristic, but humans have been dreaming about it for as long as we've been telling stories. Ancient myths are filled with heroes who fall asleep for a night and wake up years later. In the Hindu epic, the Mahabharata, there's a tale of King Kakudmi who visits the creator god, Brahma, and discovers that while only minutes passed in the heavenly realm, whole ages have slipped by on earth. In Japanese folklore, there's Hiroshima Ta, a fisherman who saves a turtle and is rewarded with a trip to an undersea palace. He spends what feels like days there, but when he returns, centuries have gone by. Even Washington Irving's Rip Van Winkle taps into the same timeless dream, the idea that time might not flow the same for everyone, that it might be cheated, bent, or skipped. And isn't that part of the charm of the whole subject? We all, at some level, want it to be true. We want one more chance to say something we didn't say, to revisit a day we loved, or maybe to skip ahead to see what's waiting. Time travel is a kind of wish machine, reflecting our regrets and our hopes all at once. Physics, with its cold equations and rigorous proofs, somehow brushes against those soft, human dreams. It says, maybe. Maybe the universe is stranger than we can bear. Let's slow down here though, before we drift too far. For tonight, we're only at the beginning of the journey. Think of this as stepping into the foyer of a strange, endless house. Ahead are corridors lined with paradoxes, wormholes, black holes, and mind-bending possibilities. But for now, we're just looking at the first doorway. The gentle truth that time isn't fixed, that it bends and flows, and that you are already, in your quiet way, a traveler. Each heartbeat, each blink, each breath is another tiny leap forward. You don't need a machine to move into tomorrow. You're already doing it, 1 second at a time. Still, the bigger leaps beckon. What if we could speed it up? What if we could find a way to slow time to a crawl for ourselves, while the rest of the universe races ahead? What if we could stretch the arrow of time like taffy, bending it, looping it, twisting it until past and future touch? Those are the questions we'll wander into next. But not tonight. Tonight, we've set the stage. We've remembered that the arrow of time isn't as straight as it looks. We've opened the door just a crack and peeked inside. And already, it's enough to remind us that the universe isn't just about what is, it's about what might be. So, as you drift off or let your thoughts wander, remember this. Time isn't rigid. It's elastic, playful, maybe even forgiving. The future is always waiting, and the past is always whispering. And between them, here you are, carried along on the strangest journey of all. Not a passenger, not a prisoner, but a traveler. Always a traveler. Let's begin with paradoxes. Those mischievous puzzles that pop up whenever we imagine moving backward in time. The most famous one we already touched on, the grandfather paradox. You go back in time, prevent your grandparents from meeting, and poof, never exist. But if you never exist, you couldn't go back in time in the first place. Which means they did meet. Which means you do exist. Which means you could go back. Which means, you see where this is going? It's like trying to fold a piece of paper that keeps unfolding itself in your hands. There's also the bootstrap paradox, which is one of my personal favorites because it's quietly unsettling. Imagine you travel back in time with a book of Shakespeare's plays. You meet young Shakespeare before he's written anything and hand him the book. He copies the plays down and publishes them under his name. They become famous, studied for centuries. Until eventually, you were born, grow up, and one day travel back in time carrying that very same book. Here's the problem. Who actually wrote the plays? Shakespeare didn't, because he copied them from you. You didn't, because you copied them from him. The book simply exists, floating in a loop, without origin. A story with no author. A piece of information conjured out of nothing. These paradoxes are fun to talk about, but they're not just word games. They highlight the deep tension between our everyday understanding of cause and effect, and what physics sometimes suggests might be possible. Most of the time, we like things neat. A causes B, causes C, drop a cup, it shatters. Say something kind, someone smiles. But introduce time travel, and suddenly effects might come before causes. Maybe the smile causes the kindness. Maybe the shattering causes the dropping. It's enough to make your head spin. So what does physics say about all this? Surprisingly, it doesn't say, impossible, stop daydreaming. Instead, some physicists propose that paradoxes simply never happen. Not because time travel is impossible, but because the universe has built-in safeguards. One version of this is called the Novikov self-consistency principle, which sounds intimidating but is basically the universe's way of saying, sure, you can go back in time, but you can't change anything in a way that creates a contradiction. You're allowed to nudge events, but only in ways that fit the overall story. If you try to stop your grandparents from meeting, something will get in the way. You'll trip on the sidewalk, or the matchmaker shows up early, or the wind blows your letter into the fire. The universe conspires, gently but firmly, to keep the timeline intact. In this view, you don't really change history. You fulfill it. If you hand Shakespeare the book, then maybe you were always destined to. The plays exist because you gave them to him, and you gave them to him because the plays exist. It's a closed loop, strange but internally consistent. Not everyone finds that idea comforting. Some find it claustrophobic, like free will itself is being smothered. But others see it as elegant, a cosmic safety net that keeps logic from unraveling. The universe doesn't like contradictions, so it ties them up in neat, if puzzling, knots. Now, let's leave paradoxes for a moment and wander into another alluring idea. If time travel has a celebrity poster, it's probably a wormhole. That hypothetical tunnel through space-time that lets you leap instantly from one point to another. Popular culture loves them portals, glowing with light, shortcuts through the cosmos. And the funny thing is, wormholes aren't just imagination. They fall out of Einstein's equations quite naturally. Mathematically, they're possible. The problem is, keeping them open is like trying to hold a door that the universe is determined to slam shut. Without something exotic like negative energy or matter with properties, we've never observed wormholes collapse before you can use them. But here's where things get really juicy. If you could stabilize a wormhole, you wouldn't just have a shortcut in space. You'd have a shortcut in time. Here's how. Imagine you take one end of the wormhole and keep it stationary near Earth. Then you take the other end, put it on a spaceship, and accelerate it close to the speed of light. Time for the traveling end slows down relative to the stationary one, thanks to relativity. After a while, you bring it back. Now, one end of the wormhole is younger than the other. Step through one end, and you come out in the past or the future relative to the other. Presto! A time machine, courtesy of cosmic plumbing, Of course, saying it is easier than doing it. The energy requirements would be absurd, the engineering beyond our imagination. And even if you did manage it, you'd still have to deal with those pesky paradoxes again. Still, wormholes occupy a fascinating place in the conversation. They're a perfect example of how time travel hovers in that twilight zone between utterly impossible and maybe, if the universe is generous. Speaking of generosity, the universe does offer one other intriguing hint that time travel might not be hopeless: black holes. These cosmic beasts are famous for swallowing everything, even light, but inside their math is a curious solution. Some versions of Einstein's equations suggest that rotating black holes might contain passages, wormholes again. In disguise, that could connect different points in space and time. It's unlikely these would be traversable, and even if they were, the tidal forces would tear you apart long before you got the chance to shake hands with your younger self. But still, the possibility is enough to keep theorists awake at night, sketching equations like treasure maps to impossible places. At this point, it's tempting to laugh and say, well, fine. Time travel is technically possible in equations, but practically impossible in reality. And maybe that's true. Maybe it will forever remain a dream, something to ponder as we stare at the stars. But then again, history has a way of humbling us. Not long ago, heavier-than-air flights seemed absurd. The idea of harnessing electricity, of speaking across oceans instantly, of peering billions of light-years away, of at once, sounded ridiculous. So when physics tells us time travel is possible on paper, maybe it's worth listening. Even if we never build the machine. And besides, the journey isn't just about machines and math. It's about meaning. Time travel forces us to wrestle with big questions. What is the past? Is it fixed, or can it change? What is the future? Is it open, or already written? And what about the present, this slippery, vanishing point we cling to? These aren't just scientific puzzles, they're human ones. They touch our regrets, our hopes, our longing for second chances. Time travel is as much about philosophy as physics. Maybe that's why stories about time travel are so enduring. They let us play with these questions in safe, imaginative ways. In Back to the Future, Marty McFly frets about accidentally erasing his own existence. In Doctor Who, the Doctor insists that some moments in history are fixed, while others are fluid. In Arrival, time isn't a line at all, but a circle, with past and future coexisting. These stories resonate because they're not just about machines, they're about us, about our desire to understand our place in the flow of time, and perhaps that's the most important thing to remember tonight. Time travel isn't just about physics bending, it's about imagination stretching. It's about taking the rigid clock on the wall and realizing it might be more like a canvas, smeared and folded, painted with possibilities. So as you settle deeper, maybe half dreaming now, let yourself wonder, what would you do if you could step backward? Whose hand would you hold one more time? What would you whisper to your younger self? Or, if you could leap ahead, what would you want to see? A world healed, a future brighter, or simply the quiet reassurance that life goes on, that time carries us forward, with or without our permission? Tonight, we don't need to decide. We just need to linger with the mystery, to imagine wormholes like hidden doorways, paradoxes like playful riddles, and the universe itself as a storyteller, weaving a plot far stranger than anything we could invent. Next time, we'll wander deeper still. We'll explore the arrow of time, why it flows forward and not backward, and whether that arrow might one day bend. But for now, rest in the knowledge that time travel, while wrapped in paradox and possibility, is already stitched into the fabric of the cosmos. Maybe not as flashy as a machine with blinking lights, but quieter, subtler, and perhaps even more wondrous. Because you're already doing it, traveling forward, second by second, heartbeat by heartbeat, into the only future you'll ever truly know. If time travel is possible, even just in theory, there's still a question that hangs over everything. Why does time, as we actually live it, always seem to move one way? Forward, never backward. We can remember yesterday, but never tomorrow. We can shuffle through old photographs, but we can't flip ahead to see the next chapter of our own story. You drop a glass and it shatters. You never see shards leaping back into a whole cup. And that one-way movement is so constant, so deeply built into our experience, that we almost never question it. But we should, because physics itself doesn't actually demand it. At least, not in the way you might think. Here's the strange part. The fundamental laws of physics, the equations that describe how particles move, how forces act, how energy flows, don't really care about direction. If you were to watch a video of two particles colliding and then play it backward, the math would still work. The rules don't mind. They're symmetric in time. Forward, backward, it doesn't matter. Which means the arrow of time, the sense that it points from past to future, doesn't come from the underlying laws. It comes from something else. And that something is one of the most profound ideas in science: entropy. Entropy is one of those words people love to throw around as shorthand for chaos. Your kitchen after a dinner party has high entropy. Your laundry pile on Sunday night is maximum entropy. But in physics, entropy is more precise. It's a measure of disorder, yes, but really, it's about the number of possible arrangements a system can have. Imagine a deck of cards. If it's neatly ordered from ace to king, that's low entropy, only one very specific arrangement. Shuffle it, and the entropy rises, because there are many more possible messy orders than neat ones. The higher the entropy, the more ways the system can be arranged without changing its overall appearance. Now, here's the crucial point. In the real world, entropy tends to increase. Not always in the short term, not always in tiny systems, but overall, on the grand scale of the universe, disorder grows. This is the second law of thermodynamics. Left to themselves, things spread out, mix together, wear down. An egg cracks. Cream dissolves into coffee. Heat flows from hot to cold. And once those things happen, they almost never spontaneously reverse. You don't see coffee leaping out of milk to separate itself. You don't see warmth in a room suddenly collapsing into one corner, leaving everything else icy. Technically, it's not impossible, it's just so staggeringly unlikely that you could wait longer than the age of the universe and never see it. Entropy is why time seems to march in one direction. Because the past is always the state of lower entropy, and the future is always the state of higher entropy. The arrow of time is, in a sense, the arrow of disorder. This explains a lot. Why you can remember yesterday but not tomorrow. Because your brain is an entropy machine. Forming a memory increases order inside your neurons but releases heat and disorder into your environment. So the memory-making process can only flow one way. Why you age? Entropy, agensals accumulate damage. Processes become less efficient. Things wear out. Why the universe looks the way it does? Entropy is the quiet sculptor. From stars burning their fuel to galaxies drifting apart. Everything is riding this one-way current dot, and yet, there's a puzzle here. If entropy is always increasing, that means it must have started low. Very low. In fact, the early universe, just after the Big Bang, was in an almost unbelievably ordered state. Perfectly smooth, perfectly dense, like a billiard table with every ball lined up. Why? Why would the universe start so improbably neat? That question keeps cosmologists awake at night. Some say it's just the way things were. Others suggest deeper principles we haven't yet grasped. Whatever the answer, that strange initial order is what allows the arrow of time to exist at all. Without it, maybe there'd be no past, no future, just a timeless soup of possibilities. Entropy also gives us a kind of time machine of its own. The ability to look back. When you see a broken cup, you know there was once a whole one. When you see smoke drifting into the sky, you know there was once a fire. The past leaves traces precisely because entropy grows. Each increase leaves behind scars, footprints, fossils. But the future? It hasn't happened yet, so it leaves no scars. That's why we can infer the past but not predict the future with certainty. It's not just a limitation of our minds, it's built into the physics of time itself. But here's where things get interesting for our time travel adventure. If the arrow of time is tied to entropy, then in principle, if you could reverse entropy, you could reverse time. If you could make coffee leap out of milk, make heat flow from cold to hot, make eggs reassemble themselves. You'd be walking backward along the timeline. The problem, of course, is that doing so would require manipulating the universe at an absurdly precise level. You'd need to control the motion of every particle, every atom, in ways so exact that even a tiny slip would ruin the whole effort. It's like trying to unscramble an egg, not with your hands, but with a billion tiny tweezers working in perfect synchrony. Possible in theory, utterly hopeless in practice. And yet, that's the tantalizing part. Physics doesn't forbid it outright. It just makes it unbelievably hard. In fact, there are tiny glimpses of time reversal hiding in nature already. On the smallest scales in the quantum world, particles sometimes behave in ways that blur the arrow of time. A particle might spontaneously decay, then reform, then decay again. Quantum processes are governed by probabilities, not certainties, and when you dig deep into the math, you find that many of them are time-symmetric. They don't care which way the clock is ticking. It's only when you step back, when you let huge numbers of particles interact, that entropy emerges and the arrow asserts itself. Time, in other words, may be less fundamental than we think. It may be an emergent property, like the sound of waves crashing. No single water molecule makes a wave, but together, they create the roar. No single atom makes time, but together, they create the arrow we live by. This raises unsettling questions. If the arrow of time is emergent, could it break? Could there be places or moments where it flips? Imagine a region of the universe where entropy decreases, where disorder gives way to order. To us, it would look like time itself running backward. Stars unburning ashes, forming into logs, rivers flowing uphill. Sounds absurd, but some cosmological models suggest that in the far future, maybe in distant corners of the cosmos, such things might be possible. Maybe time doesn't have a single arrow at all. Maybe it has many arrows, pointing in different directions, tangled like a bird's nest. And we just happen to live in one strand that points forward. Of course, it's one thing to imagine such things in the abstract, and another to live them. What would it feel like to exist in a world where time ran backward? Would you notice? If your memories also ran backward, if your thoughts unformed as events unhappened, maybe it would feel perfectly normal. Maybe you wouldn't sense the reversal at all. In that case, what does forward even mean? Perhaps our sense of moving into the future is just a trick of perspective, like feeling motionless while sitting on a spinning earth. The arrow might be an illusion, one so powerful we can't escape it, but an illusion nonetheless. That doesn't mean we're helpless. Understanding the arrow of time has practical consequences too. It tells us why perpetual motion machines, those dream devices that run forever without energy, input, are impossible. They would require entropy to stay constant or decrease, which nature refuses to allow. It explains why aging can't be stopped entirely, why even the best medicine will eventually reach its limits. And it hints at the ultimate fate of the universe. If entropy always increases, then one day, far in the future, the cosmos will reach maximum disorder, a state where energy is evenly spread, no differences remain, no structures can form. This is the so-called heat death, a silent, cold future where nothing interesting happens. Not a bang, not a crunch, but a long fading sigh. It's a sobering thought, but also a strangely peaceful one. If time has an arrow, then it also has a destination. We may not like it, but maybe that's part of the beauty, the knowledge that our universe, like us, has a story with a beginning, a middle, and an end. And yet, while entropy paints this grand, inevitable picture, there are still surprises. Life itself, for instance, seems to defy entropy. A seed becomes a tree, a single cell becomes a human, order blossoms everywhere. But this isn't really a violation. Life builds order locally by exporting disorder elsewhere. The tree grows, but in the process it burns sunlight, scatters waste, and increases entropy in its environment. You grow, but only by eating, metabolizing, releasing heat. Life is not the enemy of entropy. It's a clever collaborator, finding temporary islands of order in a sea of growing chaos. Which makes you wonder, if time's arrow is guided by entropy, maybe consciousness itself is tied to it too. Maybe the very fact that you're here, listening, thinking, remembering, is only possible because entropy increases. If that's true, then without the arrow, there's no you, no me, no story at all. Time travel, in that sense, isn't just about machines or paradoxes. It's about the conditions that make existence possible in the first place. So tonight, as we drift toward the next part of this strange journey, let's hold on to this. The arrow of time is not a law written in stone, but a whisper of disorder, a tendency, a leaning. We've talked about entropy, about the arrow of time, about the one-way flow that seems to define our universe. But time isn't just something written in equations, it's something we feel. We live inside it. And before we go chasing black holes and cosmic shortcuts, maybe we should pause and look closer at the way time travels inside us. Because, if you think about it, every one of us is already a time traveler, not in the way we usually imagine. What do I mean by that? Consider memory. Right now, as you listen, you're not just existing in the present, you're carrying the past with you. The faces of people you've loved, the songs you've heard, the moments you've laughed until your stomach hurt, all of them are stored, imperfectly, in your mind. When you remember them, you're not physically going back, but your mind is. A memory is a kind of time travel, a window into a moment that no longer exists, but is still alive in you. Sometimes the memory is clear, crisp, almost like stepping back into the scene. Other times it's blurry, fogged, unreliable, like trying to tune into a faint radio station. Either way, it's your personal time machine. One that works whether physics allows paradoxes or not. And then there are dreams. Think about how, in a dream, time stretches and contracts in ways that don't make sense. You fall asleep, and in a few minutes of real time, you live through hours, days, entire adventures. You wake up disoriented, unsure what was real and what was imagined. Dreams show us that our perception of time isn't fixed. Our brains can bend it, stretch it, compress it. Time, as we experience it, isn't just an arrow. It's elastic. Even in waking life, this elasticity is everywhere. Have you ever noticed how time seems to crawl when you're bored, every second dragging its feet like a stubborn child? And how, in contrast, hours vanish when you're deeply engaged, laughing with friends, or lost in a creative flow. Objectively, the clock ticks the same, but subjectively, time changes. It stretches in suffering, it flies in joy. Neuroscience suggests this has to do with how our brains encode information. When you're bored, your brain has less to record, so each moment feels long and empty. When you're engaged, your brain is flooded with new details. So later, in memory, the time feels dense, full, and fast. Time isn't just physics. It's psychology. And maybe that's why time travel stories resonate so deeply. Because they echo something we already know, that time is slippery. That it doesn't always behave the way we expect, at least not inside us. When you look back at your childhood, decades may have passed, yet it feels like yesterday. When you imagine the future, you sometimes feel like you can almost touch it, almost reach out and pull it closer. Our minds are already bending time every day. But memory, dreams, perception, they also show us the limits of our time travel. Memory fades. Dreams dissolve. Perception tricks us. We can visit the past in our minds, but never with perfect clarity. We can anticipate the future, but never with certainty. And perhaps that's why the fantasy of physical time travel is so seductive, because it promises to break those limits. To not just imagine yesterday, but to touch it. To not just hope for tomorrow, but to see it. Of course, there's a darker side too. If time travel reflects our longing for second chances, it also reflects our fear of inevitability. We all have moments we'd undo if we could. Words we wish we hadn't said. Chances we wish we'd taken. Losses we'd do anything to reverse. Time travel stories let us play with that fantasy. What if we could go back, stop the accident, say the thing we never said? But deep down, we know the truth. The past is gone. The glass doesn't the person doesn't unleash. And so time travel becomes both comfort and torment. A door we dream of opening, even as we know it may never exist. It's not only regret though. Time travel is also about hope. When we dream of jumping forward, It's not just curiosity. It's longing. To know that things will be okay. That the world will survive. That our loved ones will be happy. That the struggles of today will matter in the long run. A leap into the future, even just for a glimpse, would be the ultimate reassurance. That's why fortune tellers, prophecies, and predictions have always had such a grip on us. They promise what time withholds. Knowledge of tomorrow, science, in its own way, has already given us glimpses, not with crystal balls, but with light. When we look at distant galaxies, we are literally looking into the past. Because their light has taken millions or billions of years to reach us. The night sky is a time machine. One we use without even realizing it. Every star is history, every photon a messenger. Some of those stars may already be dead, extinguished ages ago. But their light is only just now arriving, fooling us into seeing them alive. The cosmos tricks us, showing us ghosts of the past in the present. It's humbling, and a little eerie. But if we can look into the past with light, can we ever look into the future? Not directly, not yet. But we can predict. Physics lets us project forward, charting where planets will be, when eclipses will happen. Even how the universe itself might evolve. These predictions are precise, reliable, but only for simple systems. For complex ones, like weather, or like human life, prediction quickly collapses into uncertainty. The future refuses to be pinned down, which is probably why we cling so tightly to stories of machines that can take us there. Because prediction isn't enough. We want to see it with our own eyes still. Maybe the most shocking truth is this. You don't need a machine to be a time traveler. You already are one. Your mind, with its memories and dreams, carries you backward and forward every day. Your body, aging, changing, is a vessel moving through time. Every step you take is a step into the future. Every breath you breathe is irreversible, carrying you forward. Time travel isn't an invention waiting to happen. It's the condition of existence. And maybe, just maybe, that's the real reason we tell these stories. Not because we think we'll one day build a machine that spins us through centuries, but because time itself is already the strangest machine of all. Because it teases us with memory, blinds us with uncertainty, and yet carries us relentlessly onward. And because, by dreaming of breaking free, we remind ourselves of how precious the flow really is. So let's hold on to this thought as we prepare to leave the realm of memory and perception and step back into the vast machinery of the cosmos. The black holes, the cosmic strings, the wormholes, the places where time isn't just something we feel, but something written into the very geometry of the universe. We've seen how time bends inside us. Next, we'll see how it bends out there, on scales so vast they make our lives feel like whispers. For now, though, rest with this, you are already a time traveler. Maybe not in the way of science fiction, but in the truest way possible. Through memory, through hope, through perception, through every heartbeat. You are moving through time, carrying your past, reaching toward your future. And that is no less extraordinary than any machine we could imagine. When we've been talking about time travel so far, much of it has been gentle, almost abstract. Wormholes in chalkboard equations, paradoxes whispered like riddles, entropy ticking quietly in the background. But if you really want to see time stretch and warp, you don't have to rely only on thought experiments. You just have to look out into the cosmos. Because the universe, in its wildest corners, is already a kind of time machine. The trick is getting close enough to use it and surviving the trip. Let's begin with black holes. Those monsters of space-time that seem designed to make humans feel small. You probably know the basics. A black hole is a region where gravity is so intense that nothing, not even light, can escape. Fall past the event horizon, the invisible boundary surrounding it, and you're gone, lost to the outside universe. But what's less obvious, and maybe even stranger, is what black holes do to time itself. Imagine hovering safely just outside the event horizon. To you, time would feel normal. Your watch ticks, your heart beats, seconds pass the way they always do. But to someone far away, watching you through a telescope, things look very different. They would see you slow down. Your movements would stretch out, your signals drag. As you approached the horizon, you'd seem to freeze, suspended in time. Your last image smeared into red and fading into darkness. From their perspective, you never quite fall in. You just fade away, asymptotically frozen at the edge. From yours, though, you cross the line and plunge inward, and time flows as usual, at least, until tidal forces tear you apart like cosmic spaghetti. This time warping isn't just a curiosity. It's a vivid demonstration of relativity. The stronger the gravity, the slower time flows. Near a black hole, hours for you might be years for someone watching from afar. In fact, this idea was dramatized beautifully in the film Interstellar. The astronauts land on a planet orbiting close to a supermassive black hole. They spend just a few hours on the surface, but when they return to their ship, they discover decades have passed for their crewmate waiting above. The movie took some liberties, of course, but the principle is sound. Gravity is a natural time machine. If you can get close to something massive enough, you can leap into the future simply by waiting. But there's always a catch. Black holes aren't exactly hospitable vacation spots. Venture too close, and the difference in gravity between your head and your feet, the tidal force, becomes unbearable. For small black holes, this happens well outside the horizon. You'd be stretched and torn apart long before you got a chance to enjoy your time-warping holiday. For supermassive black holes, the tidal forces at the horizon are gentler. So you could cross without noticing, at least at first. But then, inevitably, the singularity awaits. That place where our equations break down, and no one knows what really happens next. Some theorists whisper that maybe, just maybe, singularities connect to other places or times. Maybe falling into one is less an ending and more a doorway. But for now, that's speculation. Math-chasing mysteries we're not yet equipped to solve. Black holes aren't the only cosmic machines that toy with time. There are stranger, more hypothetical beasts still lurking in theory. One of them is the cosmic string, not to be confused with the kind that tangles in your drawer. These are hypothesized defects in spacetime itself, left over from the early universe. Imagine a thread thinner than an atom, but stretching across galaxies, incredibly dense, incredibly powerful. If two cosmic strings were to pass by each other at high speed, the distortion in spacetime could, in principle, create closed time-like curves, loops in time. In other words, if cosmic strings exist, and if you could find and harness them, they might form the basis of a time machine. The math allows it. Reality, so far, has not obliged us with any evidence that cosmic strings are real. Still, they linger in the equations like ghost notes in a song, tempting physicists to wonder, what if? And then, there are rotating universes. We usually imagine space as static in its geometry, expanding outward maybe, but not spinning like a carousel. Yet, in 1949, the mathematician Kurt Gödel found a solution to Einstein's equations that described a rotating cosmos. In such a universe, closed time-like curves appear naturally. You could, in theory, travel along a certain path and arrive back at an earlier point in time. The catch: Gödel's universe doesn't look much like ours. Observations show that our cosmos isn't rotating in that way. Still, his solution is a tantalizing reminder that relativity has more flexibility than our imaginations often allow. Even without such exotic constructs, you don't have to go far to see time already being bent. Your GPS system, the thing in your phone that tells you where to turn left, has to account for relativity. Satellites in orbit experience weaker gravity than we do on Earth's surface, so time runs slightly faster for them. But because they're also moving quickly, time simultaneously runs slightly slower. Engineers have to combine both effects, adjust the clocks on the satellites, and correct the signals. Otherwise, the system would drift by kilometers every day. In other words, without accounting for time travel, tiny, subtle, but real, you wouldn't find your way to the nearest coffee shop. All of this suggests something humbling. Time travel isn't only a speculative dream about far-off wormholes or impossible machines. It's woven into the fabric of the cosmos right now. Gravity warps it. Speed stretches it. Black holes magnify it. Satellites correct for it. Time isn't a rigid river, but a malleable fabric, and the universe is constantly tugging at it. The challenge isn't whether time travel exists, The challenge is whether we can learn to harness it in dramatic ways. The kind that let us leap across centuries rather than milliseconds, and maybe, just maybe, those dramatic ways come with dangers we haven't even begun to imagine. Think of causality, the chain of cause and effect that underpins everything. Our lives make sense because events line up. You plant a seed, a tree grows. You press play, a video begins. But time travel on cosmic scales threatens to unravel that chain. If you could leap into the past, even indirectly, through some exotic black hole passage, would cause and effect still hold? Or would the universe stitch events together in ways that defy our logic? Some physicists argue that paradoxes wouldn't happen, that consistency would always win. Others argue that paradoxes point to deeper truths we haven't uncovered yet. Maybe even alternate timelines, branching like rivers. It's dizzying to think about. One moment you're orbiting a black hole, watching centuries slip by outside. The next, you're contemplating a universe that spins in circles, dragging time with it. And yet, despite all the strangeness, there's something grounding here too. These aren't just fantasies. They emerge from the same equations that describe why apples fall and why planets orbit. Einstein's relativity isn't an invitation to daydream. It's a description of reality, tested, verified, confirmed again and again. And in that reality, time bends. So what does this mean for us? Tucked away on our small blue planet, far from cosmic strings and safe from black holes. Maybe it means that time travel isn't something to build. Maybe it's something to notice. Every time an astronaut returns home, a fraction of a second younger than they would have been. Every time a satellite sends a signal corrected for relativity. Every time we look at the light from a distant star, carrying news from millions of years ago, we are already, constantly, participating in time's flexibility. The machines may not look like DeLoreans or glowing portals. They may look like telescopes, rockets, and clocks. And maybe that's the deeper lesson here. Time travel isn't about breaking the universe. It's about understanding it. It's about realizing that time is not absolute, not fixed, but as pliable as clay. We may never build a machine to step into yesterday. We may never ride a cosmic string into a loop, but by recognizing that time is flexible, we already live in a universe stranger than any fiction. As we close this part of our journey, imagine yourself standing on the edge of a black hole, staring at the horizon. To you, it's just another second ticking by. To the universe beyond, ages slip past in a blink. You are one traveler in a cosmos full of clocks, some fast, some slow, all ticking differently, yet all part of the same strange story. And in that story, time travel isn't a destination, it's already here. Next time, we'll step into even more unsettling territory. The possibility of multiple timelines, alternate histories, and whether the universe itself branches into countless versions every time a paradox threatens to appear. But for now, rest with this thought. You don't need a time machine to see the future. It's written in the stars above you, their light carrying whispers from millions of years ago. You don't need to bend time to touch the past. It's already in your eyes, in the photons falling gently onto your retina tonight. By now, you and I have wandered through black holes, entropy, wormholes, and paradoxes. We've stretched time with gravity and bent it with speed. But still, one of the thorniest problems hangs in the air like a puzzle you can't quite put down. If time travel into the past is possible, what about paradoxes? How can the universe allow them? How can logic survive if you go back and step on a butterfly that was supposed to flutter and feed a bird that was supposed to sing and inspire a poet who was supposed to write the book you once read? This is where one of the most fascinating and unsettling ideas steps onto the stage. Alternate time. The suggestion is simple, and yet dizzying. Maybe paradoxes don't happen because the universe doesn't just have one timeline. Maybe every time you act, every time you make a choice, reality branches. One version where you did step on the butterfly, another where you didn't, one where your grandparents met, one where they didn't, one where you're listening to this voice right now, and maybe unsettlingly one where you aren't. This idea didn't come out of nowhere. It has roots in quantum mechanics, the strange science of the very small. Quantum mechanics tells us that particles don't always have definite properties until they're measured. An electron, for example, can behave as if it's in multiple places at once, a blur of probabilities. When you measure it, you get one definite outcome. But here's the twist. What happens to the other possibilities? Do they just vanish, like soap bubbles popping? Or do they continue to exist somewhere else, in another branch of reality? In 1957, physicist Hugh Everett proposed what's now called the many worlds interpretation. He suggested that all outcomes happen every time a quantum event could go one way or another. The universe splits. One branch where the electron lands here, another where it lands there. Both are real, both continue. Multiply this across the vast ocean of quantum events happening every second, and you get an unimaginable branching tree of universes, each one as real as ours, each one diverging endlessly. If Everett was right, then paradoxes might be no problem at all. Step into a time machine, travel to the past, and make a change, and all you've done is slip into a different branch. You can't erase your own existence, because in your original branch, you already existed and lived your life. All you've done is hop over into the branch where things unfolded differently. Your grandparents might not meet there, but in another timeline, they did. Both are consistent, both coexist. Both part of the ever-branching multiverse. It sounds elegant, but also a little overwhelming. Imagine infinite versions of yourself, making infinite choices. One version of you turned left instead of right this morning. Another picked tea instead of coffee. Another never heard this story at all. Another is listening right now, but in a universe where the stars above shine slightly differently. Because the early universe branched in its own way. It's almost too much to hold in the mind. Like staring at a fractal that keeps expanding, no matter how closely you look. And yet, there's something oddly comforting in it too. If every possibility exists somewhere, then maybe nothing is ever truly lost. The road not taken wasn't abandoned. It just split off, carried forward in its own universe. Every regret you've ever had, every what if, is playing out somewhere. Every hope you've ever imagined might be real in some other branch. It's a strange kind of immortality. Not for your body, but for your possibilities. But let's not get carried away just yet. Many worlds is elegant, but it's not universally accepted. Some physicists love it. Others find it extravagant, multiplying universes without necessity. They ask, if these other branches exist, why can't we see them? Why can't we communicate across them? If a version of me is recording these words in another branch, why can't I wave to them across the divide? The answers vary. Some say the branches are forever separate, like parallel train tracks that never meet. Others suggest subtle interference patterns might someday hint at their presence. For now, it's speculation, beautiful, haunting speculation, but still unproven. Even so, the idea has seeped into our culture. You see it in movies like Sliding Doors, where a single missed train spins to different stories. In Avengers Endgame, where time travel creates alternate realities rather than paradoxes. In countless novels, comics, and thought experiments. We're drawn to the multiverse because it solves a problem, but also because it scratches a deep itch in the human heart. The longing for second chances. The curiosity about what might have been. And if you think about it, the multiverse isn't just science fiction. Every decision you make feels like a kind of branching. In one sense, only one outcome is really chose coffee, not tea. But in another sense, the unchosen option lingers, a ghost of possibility in your mind. Many worlds just takes that feeling and gives it teeth, suggesting those ghosts aren't just memories of what didn't happen, but realities of what did, somewhere. So, what does this mean for time travel? If many worlds is right, then stepping into the past doesn't risk unraveling your own existence. Instead, it means your creator, rather, enter an alternate timeline. You can meet your grandparents, stop them from marrying, and live in a universe where you were never born. But the original timeline, the one you came from, still exists. You just can't get back to it. You're a traveler, lost in a neighboring branch, forever cut off from the road you started on. That might sound exciting, but also a little tragic. Time travel, in this sense, is less about changing your past and more about abandoning it. You can't undo your mistakes in your timeline. You can only create a new one where those mistakes never happened. You can't return to the childhood you remember. You can only visit a similar one in another branch, where the details are almost the same but never quite. And yet, even that is astonishing. Imagine standing in a world almost identical to yours, except one small change rippled outward. A world where a single historical event went differently, where a war was never fought, where a discovery was never made, where a single word in a conversation changed the course of lives. Every alternate history novel you've ever read might not just be fantasy, it might be a glimpse into another branch. Of course, the multiverse raises just as many puzzles as it solves. If there are infinite versions of us, are they all equally real? Do they all matter? Is there a moral weight to choices if every outcome happens somewhere? These aren't just physics questions. They're philosophical ones, ethical ones, and they remind us that time travel isn't only about machines and math. It's about meaning, about identity, about what it means to be you in a universe of endless variations. It also raises a playful thought. If there are infinite versions of you, some of them must be listening to this right now in other branches. Some might have paused it. Some might have drifted off to sleep halfway through. Some might never have found it at all. But you, this version of you, in this moment are here, following this story along your timeline. And that makes this moment unique. Out of infinite possibilities, this one is yours. The idea of branching universes is both comforting and disorienting. Comforting because it removes paradoxes. Disorienting because it multiplies reality beyond imagination. Maybe that's why it feels so right for time travel. Because time travel itself is always both comforting and disorienting. A dream of second chances, but also a disruption of the order we cling to. So, as we close this part of our journey, let's leave with a thought. Maybe time isn't a single arrow after all. Maybe it's a tree, branching infinitely, growing in every direction at once. Each branch a timeline, each twig a possibility, each leaf a universe. And you, sitting here tonight, are perched on one of those branches. But perhaps, just perhaps, there are other users, sitting on neighboring branches, hearing these same words in slightly different ways. Next time, we'll ask an even harder question. If time can branch, if timelines can multiply, what does that mean for free will? Are we choosing, or just walking along predetermined branches? Is time a river, a tree, or something else entirely? That's part 7. But for now, rest with this thought. The multiverse may be vast, but this moment, this branch, this you, is unrepeatable, and that makes it precious. So far, we've wandered through paradoxes, wormholes, black holes, cosmic strings, entropy, and even multiverses. We've looked outward, into the vastness of the cosmos and the bizarre rules that govern time at its edges. But now we need to turn inward, towards something more personal. Because beneath every equation, every speculation, there's a question that time travel always seems to poke at. The question of choice, of free will. If time can bend, branch, or loop, then what does that mean for us, the little travelers carried along by its current? Are we making choices, or are we simply passengers on a track laid out long before we took our first step? It's a question that keeps philosophers as busy as physicists. And maybe it keeps us awake at night, too, staring at the ceiling, wondering if we could have done something differently, if our mistakes were inevitable, or if we could have chosen another road. And in the context of time travel, it becomes sharper. If the past can't be changed, if the universe enforces consistency, then maybe everything we do was always going to happen exactly as it does. Every laugh, every heartbreak, every quiet moment of listening to this voice sit, was all written in the script. If that's true, then free will is just an illusion. A story we tell ourselves as the arrow of time carries us forward. That idea has a name: determinism, the belief that every event is the inevitable result of prior causes, stretching all the way back to the beginning of the universe. In a deterministic universe, the future is already baked in. It just hasn't been revealed yet. You're like a character in a novel, reading page after page, not realizing the ending has been printed all along. The surprise is yours, but not the author's. Physics, at least the classical kind, often leans in this direction. Newton's laws, for instance, describe a universe where, if you know the position and velocity of every particle, you can predict everything that will ever happen, down to the smallest detail. The universe becomes a grand machine, ticking with perfect inevitability. But quantum mechanics complicates that neat picture. At the quantum level, events aren't certain. They're probabilistic. An electron doesn't have a definite position until it's measured. Radioactive decay happens unpredictably. One atom here, another atom there, with no way to say which will go first. The universe, at its core, seems to have an element of chance, of randomness, and some take this as a rescue for free will. If the future isn't predetermined, then maybe we really do have choice. Carving paths into the unknown with every decision. But randomness alone isn't the same as freedom. If your choices are determined by dice rolls of quantum probability, does that make you free or just subject to chance? True free will, the kind we feel in our bones, seems to require something more. Not just randomness, not just determinism, but agency. The sense that we, ourselves, can decide. That we're not only carried by the current, but sometimes steering the boat. Time travel makes this tension even sharper. Imagine stepping into a time machine and visiting the past. If determinism is true, then everything you do there was already part of history. You didn't change anything. You simply fulfilled the role you were always meant to play. That's the Novikov self-consistency principle in action. The past is fixed, and you are woven into it. In that case, free will is an illusion. You couldn't have done otherwise, because the timeline demanded you do exactly what you did. Now imagine the many worlds interpretation. Travel to the past, make a choice, and instead of breaking history, you create or join an alternate branch. In one branch, you saved the butterfly. In another, you didn't. Both exist. But if every choice you could make exists somewhere, then are you really choosing, or are you just one of countless versions of yourself, each acting out every possibility? Free will, in this view, might be preserved locally. You feel like you made a decision, but globally. Across the multiverse, everything happens anyway. Choice becomes diluted, spread across infinite branches. It's like ordering at a restaurant where the waiter brings you every dish on the menu. One to each of your infinite selves. Did you choose the lasagna? Yes, but also, no, because another you is eating the soup. Another is stuck with the salad. Another ordered dessert first. The illusion of choice remains for you, in this branch. But, in the big picture, all outcomes exist, whether you decided or not. And yet, here's the curious part. Despite all these theories, despite all the possible ways the universe could undermine free will, we still feel it. We still wake up each day, and decide whether to hit snooze, what to eat, who to call, how to spend our time. That subjective experience of choice is undeniable, even if the physics beneath it whispers otherwise. Maybe free will is emergent, like time itself. Not fundamental, but real enough at the level we live. A wave crashing on the shore may not be fundamental. Either it's just molecules moving under gravity and wind, but it's still real to us. Maybe choice is like that. The feeling of steering, even if deep down the current was always set. This tension has shown up in stories too. Think of films where the hero tries to change the past but ends up causing the very events they were trying to prevent, destiny masquerading as choice. Or stories where alternate timelines flourish, each choice birthing a new reality. Both possibilities reflect our own inner tug-of-war. Are we free, or are we bound? And maybe both are true in different ways. Depending on how you look. Here's another angle. Time travel itself might be the ultimate test of free will. If we ever built a time machine and could travel to the past, the outcome might answer the question. If paradoxes are forbidden, if history resists change, then determinism wins. If branching timelines emerge, then maybe free will wins or at least survives in some form. And if neither happens because time travel proves forever impossible, then maybe the universe is telling us the question itself is a kind of illusion. A riddle with no solution. It's enough to make your head ache in the best way. But maybe we don't need a perfect answer. Maybe it's enough to hold both possibilities lightly. To know that physics might suggest we're determined, but our lived experience insists we're free. And maybe the truth lies somewhere in the middle, like a dance between inevitability and choice, between structure and improvisation. The music plays, the rhythm is set, but we can still move in our own way. Make it ours. Isn't that, in some sense, the gift of time itself? Not knowing. The future, always a little uncertain, the past always just out of reach. Time travel, whether real or not, shines a light on that mystery, reminding us how fragile and precious each decision feels. Maybe free will is real, maybe it isn't, but the experience of choosing is undeniable, and in the end, perhaps that's enough. So tonight, as we close this part of the journey, let's let the question linger. Maybe you're steering, maybe you're floating, maybe it's both. But either way, here you are, in this moment, listening, existing. And whatever the physics says, that feels like a choice. Next time, in our final chapter, we'll pull the threads together. We'll look at what time travel really means for us, not just in equations, but in our lives, our hopes, our stories, the paradoxes, the possibilities, the poetry of it all. But for now, rest with this thought. Whether you're free or bound, determined or choosing, you are here. And this moment, this choice to listen, makes you a traveler through time in the most important way of all. We've wandered a long way together. 8 parts, hours of thought, from Einstein's clocks to the whispers of the multiverse. We've dipped into wormholes and fallen toward black holes. Felt entropy tug at the arrow of time, wrestled with paradoxes, and asked whether our choices are truly ours. And now, here we are, at the end of the journey, or, maybe, like time itself, at a loop that might just circle back again. Tonight isn't about new puzzles. It's about stepping back, looking at the whole strange landscape we've crossed, and asking what time travel really means for us, not just in equations, but in our lives. Because for all the talk of wormholes and cosmic strings, the real fascination with time travel isn't about machines. It's about longing. It's about the ache for yesterday, the pull toward tomorrow. Every story we've told about time travel, from ancient myths to modern films, carries that same heartbeat, the wish for one more chance, or a glimpse of what's coming. We want to revisit the laughter of a childhood afternoon. We want to peek at the futures we'll never live to see. Physics gives us tools and equations, but the dream behind them is human. Time travel is a mirror for our regrets and our hopes. Think of paradoxes, the grandfather paradox, the bootstrap paradox. On the surface, they're puzzles about logic, but underneath, they're stories about agency, about what it means to change, or not change, the things that matter. The paradox isn't just whether you could stop your grandparents from meeting. It's the deeper ache of wondering whether you could undo the hurts, the mistakes, the losses in your own life. And the answer, hidden in the physics, is complicated. Maybe you can't. Maybe the past is fixed, a story already told. Or maybe you can, but only by stepping into another branch, another world, leaving your own forever behind. Either way, the paradoxes remind us that the past is slippery, and that longing for control over it may always be just out of reach. Wormholes and black holes, on the other hand, aren't really about regret. They're about awe, about the dizzying possibility that the universe itself contains shortcuts, doorways, hidden pathways through space and time. They tell us that the cosmos is stranger and more generous than we can imagine. That time isn't a rigid wall, but a pliable fabric. Every black hole, every warped clock, is a reminder that time isn't absolute. It bends, it stretches, it slows. That's not just science, it's poetry, written into the stars themselves. Entropy. The arrow of time pulls us in another direction. It reminds us that time isn't just about bending, it's about flow, about the one-way march toward disorder. The increase of entropy that makes broken cups stay broken and memories flow backward, not forward. Entropy gives time its texture, its rhythm. Without it, there'd be no past, no future, just a static, timeless blur. And entropy tells us something else too, that our lives are carved into the flow of time itself. Every laugh, every tear, every thought is part of that great current, an eddy in the stream. That can feel sobering, knowing the universe is sliding toward heat death, but it can also feel strangely comforting, because it means the arrow of time isn't just carrying us away, it's carrying us forward, together, into the great unfolding. Then came the multiverse. The many worlds interpretation, alternate timelines, branching like trees. Here, paradoxes dissolve, but so does certainty. Every possibility plays out somewhere. Every choice is made, every road taken. In one universe, you're listening right now. In another, you paused. In another, you never found this at all. That idea is disorienting, yes, but also tender, because it means the roads not taken aren't lost. They're real, somewhere. Every what if has its place, and maybe that's the closest thing to immortality we'll ever know. Not that we live forever, but that every version of us exists, scattered like stars across a multiverse of possibility. And then, free will. The question of whether we're choosing our paths or simply playing roles in a script already written. Determinism whispers that the future is fixed, the past immutable. Quantum mechanics replies with dice rolls, probabilities, uncertainty. The multiverse muddies the waters further, suggesting that maybe every choice happens anyway. And yet, through all of it, we still feel free. We still feel like we're steering, even if the current was set from the start. Maybe free will, like time itself, is emergent, not fundamental, but real enough. Real enough to matter, real enough to make life worth living. So what do we make of all this? After hours of wondering, what can we carry with us? Maybe it's this: time travel, whether possible or not, teaches us to see the present differently. It reminds us that time is not a given, that the seconds slipping by right now are precious, unrepeatable, that the past we long for and the future we imagine are both illusions. In a sense, because the only place we ever live is here, now, this moment, this heartbeat, this choice to listen. That doesn't mean the dream of time travel is meaningless. Far from it. It's one of the most powerful dreams we have, because it lets us reflect on what matters most. If you could go back, what would you change? If you could go forward, what would you want to see? Those questions reveal our hearts more than our science. They tell us what we value, what we regret, what we hope for. And maybe that's the true power of time travel. Not in building a machine, but in imagining one. Not in bending space-time, but in bending perspective. Look around you right now. The light you see from the stars is time travel. The photons hitting your eyes tonight left their homes thousands, millions, even billions of years ago. To look at the night sky is to look into the past. Every star is a time capsule, carrying history across the darkness. Even the light from our own sun is 8 minutes old. When you feel its warmth on your skin, you're feeling the past. The universe is already a time machine. You just have to notice, and maybe, if we stretch our minds far enough, we'll realize that we don't need wormholes or paradoxes to be travelers. We already are. Every breath carries us into the future. Every memory carries us into the past. Every story, every dream, every act of imagination is a kind of time travel. And the beauty of it is that you don't need exotic matter or infinite energy. You just need to be alive. So as we close this long journey, let me leave you with this. Time is not a prison. It's not a straight line, or a single arrow. It's a mystery, a dance, a story we're still learning how to tell. Maybe we'll never build a machine to step into yesterday. Maybe we'll never surf the currents of wormholes into tomorrow. But we don't need to, because we already have the most extraordinary time machine of all, ourselves, our memories, our hopes, our choices, our ability to look at the stars and see not just what is, but what was and what might be. So tonight, let the dream of time travel be what it's always been, a mirror, a way of seeing the past more tenderly, the future more vividly, and the present more clearly. You are a traveler. You always have been, and no paradox, no wormhole, no equation can take that away. Thank you for walking through time with me. Wherever you are, whenever you are, may the seconds ahead be kind. The memories behind be gentle, and the journey itself remind you that you are, in the deepest sense, timeless.